So I'm Dr. James Thomson. I work at ELODIZ, and I work as part of the H2020 consortium called Charisma. And we're mainly focused on the harmonization of Raman and trying to make there be a much broader interoperability across Raman units, from production lines to research, etc. So the main point of this is to help you be acquiring good data, because obviously if you're not acquiring good data, it's very difficult for you to be able to compare to other instrumentation. So just a couple of housekeeping notes. This webinar is recorded, so it's currently being recorded. All of your cameras and microphones should be automatically off, so there's no need to worry about that, but just letting you know that this is going to be recorded. As it's being recorded, we've disabled the questions panel, because just so that this can then be published later on down the line without lots of stops, so it's easier viewing for people who want to watch this in the future. That being said, we will do questions at the end, so if you have questions, feel free to type them in the chat, and we'll go through and have a look at those at the end of the presentation. And we are just about to get, I think, about half the registrants. So I think we'll probably start, because it's unfair to keep you all waiting. So let me just remember how to do everything. So we do have a couple of polls. So, oops, change my settings. There we go. We'll start with the first poll now. The second poll will come in later. The results will be displayed as a percentage of the total attendees, and they don't include your individual information, so bear that in mind. So you don't have to worry about that when you're answering these questions, but we only have a couple of polls, and they shouldn't be particularly difficult for you. If we can have the first poll, there we go. So this is just a poll on what is your experience with Raman. Just kind of tells me how long to spend on the first couple of slides that I have for you guys. So if you could just quickly answer that, that would be fantastic. So we'll keep this open for sort of a minute, 30 seconds, something like that. So hopefully we've got some results. There we go. Oh, that's good. We've got a nice array of expertise. We've got a nice amount of intermediate people. Okay, that means I will probably spend a very short amount of time on the first couple of slides. So I will just share my screen again. So the first slides, as you can tell, as to why that was the first poll, is what is Raman spectroscopy. So a lot of you, I imagine, know it's a vibrational spectroscopy technique. You're generally looking at covalent bonds. The expert users will understand that that's not a complete statement, but for the most part, that's what you're looking at. And there are 6 main vibrational modes that you look at. And so just a quick example of these, quite a lot of you have probably seen diagrams similar to this. And so you have stretching, both asymmetric and symmetric, bending in plane and bending out of the plane, again, symmetric, asymmetric. So you have this nice sort of matrix of different vibrational modes. And just a quick example using cyclohexane, you can see there are several different vibrational modes here, which are what we're actually seeing as these different peaks. And that's what allows us to fingerprint a chemical. So we end up with the Raman fingerprint region. So this talk is really to get people understanding what they need to be looking out for, complications that they can end up having. There's some indication on how to resolve these issues. And really, this is to help you to develop a methodology around avoiding errors, especially because there's not one fix for Raman. It's not a case of just do this. There are some helpful tips, but really it comes down to a combination of your equipment and your sample, and that's what you need to use to decide how you're going to use how you're going to acquire data. So the most common error that we see is no signal, and obviously very easily resolved. Open the shutter to your probe, turn your laser on, make sure your interlock is disengaged or engaged, and it's a very simple resolution. I imagine those of you with students have had to solve this problem probably sometime this week. But really what we need to do is we need to focus on our acquisition parameters. So two of the main ones are, or possibly the two most important ones, are the laser power and the acquisition time. So some samples, if you're using high laser power, especially if you're using a near infrared laser, you can end up causing damage to your samples. And what you really are looking to improve is your signal to noise ratio, so that you're getting a good, strong signal compared to the amount of noise that your system has inherently. And you can see here, I've got a couple of graphs which are showing how that can be improved with just increasing the acquisition time or increasing the laser power. It is worth noting that in some spectrometers, when you end up increasing the acquisition time, especially to much larger numbers, you end up increasing the amount of noise that you have, so you get diminishing returns there. And it's always best to start at a low laser power, especially with a sample that you've never analyzed before, and then work your way up, again monitoring for any damage that you are causing, and setting your acquisition time so that you're not saturating your detector. Preferably work in the sort of 70–80% dynamic range for your spectrometer, but working lower with a good signal to noise is not a problem and is sometimes preferred. The other very important acquisition parameter is making sure that your sample is in focus. This is much easier, I generally feel, for people that are using probes, because what you will do is Raman focus, which is where you adjust the distance between your optics and the sample to maximize the Raman peaks. The temptation when you're using a microscope system is to put it in optical focus with what is usually your camera, and then just take your Raman spectrum, assuming that it's in focus. But unfortunately, the microscope camera and the spectrometer are not always perfectly aligned in focus. So the depth of your analysis may also mean that you actually want to be slightly defocused depending on your system. So just using optical focus is not a good idea. Optical focus will get you near the point, and then using Raman focus to complete your focusing on the sample is probably better. So I'm going to briefly talk to you about background. Background can get confusing. You get a lot of papers where people are referring to like fluorescence background. Fluorescence isn't a background. It's part of the scattering from your sample. You can create a fluorescence baseline, but the background, as we're talking about it, are essentially environmental emissions. So lights are a good one, which can be visible to your spectrometer. Again, if you're working in a lab that has windows, then natural light can also be an issue. Also, the spectrometer noise makes up part of the background, and you should take background measurements, which in some systems are called dark measurements, But with the spectrometer open, so the optical path, so the path from the sample to the spectrometer completely open, the laser off, and using the same acquisition parameters that you did when you took the analysis of the sample. This will mean that you're not adding noise or creating other issues. One of the things that you need to be aware of, though, is not to just look at your background subtracted data, but to have a look at your raw data, because you can end up seeing things like this, where you see these flat tops on the peaks, and that is because you have saturated the detector in these regions. And again, these, oh, no, I deleted the picture of the lights for this one. These are, again, these high saturating peaks are just the lights. And these can end up creating negative peaks or even hiding some of your actual Raman data. And so that can lead to sometimes under subtracted background, so where you still have these peaks, which you may believe that these are actually Raman peaks and start analyzing them. So it's, again, always good to look at your background scan to check if any of the peaks that are still present in your sample spectrum after background subtraction are actually present in that, and that you can see that there's been an under subtraction in your data. And again, over subtraction, where something's moved, something has either unblocked the light, or maybe clouds have moved, so the daylight has got stronger in your lab. And so you end up with these negative peaks, which again are something that require resolution, and you need to make sure that you're aware of these. I simply did these by moving myself in and out of the line of the light to the sample. And so that's also something to be aware of. You moving yourself can change the background that is seen by your spectrometer. One of the best ways to avoid this is to have either a dark enclosure, or in this case, we have an interlocked box, beautifully constructed by ELODIZ, which is designed, this is designed for a microscope system, and it can also act as a safety device, making sure that you're not likely to get any laser scatter to the eye, especially on reflective samples, etc. Another issue that we see quite a lot are signals from holders. So again, those of you with microscope systems will possibly or probably have microscope glass slides. And so sometimes when you have a small sample, it may make sense to you to put the sample on your glass slide. But as you can see here, these are two spectra of polystyrene. One of these, the polystyrene was put on top of some glass, and the one of them it wasn't. And you end up with this photoluminescence structure from the glass coming through and distorting some of the peaks, which again will affect the analysis of your spectrum. Another one that we see, and this one's obviously much more with handheld and probe devices, is you can end up just putting a sample on a table and analyzing it directly. Now you're going to possibly get scatter from your table. Another thing that you can do is end up burning your table, especially because quite a lot of handhelds tend to be in the near infrared region, and that will just upset your lab manager. And as I run the lab here, don't do it, please. So the solution for this is really to have Raman inactive holders. So what I've tried to demonstrate here is what I call an empty space holder, which is essentially a tube that you can sit your sample on top of, so that the light can pass through the sample out the other side and doesn't interact with the holder. That way you can be relatively certain that the scatter that you're getting is just from your sample and not from the holder or anything else. So you need to make sure that there's a good distance there. Another method that you could use is by wrapping one of those glass slides in tinfoil or using some other kind of metal holder. Now this obviously presents a laser issue. You may get reflections, so this is obviously better if you've got an enclosure and laser safety goggles. You should always have laser safety goggles nearby at the very least when you're performing Raman spectrometry. But it is a solution, as you're not going to get scatter from the metal in this case. This is less signals from holder. It's the issue is what is holding your sample is moving. So if the stage is drifting slowly out of focus, or the sample is slightly moving because maybe it's slightly sloped and is rolling away, you can end up getting a loss of signal, which, especially if you're doing several accumulations over a long period of time, then you won't see that. What you will just see is the resulting spectrum. And so then you may refocus and do it again. And if your stage is still moving, you'll get the same results and you'll think that you'll have very weak scatter. So always make sure that things like stages are locked in place once you've found your optimal position, and that your sample isn't moving, especially when you get spurious data with very weak scattering that you don't expect. So the next thing I'm going to talk about is your spectrum intensity, and issues and problems that we can face with having good or a strong spectrum intensity. So when I'm talking about the spectrum intensity, again, I'm really talking about the signal to noise ratio. So having strong peaks compared to your noise, so that they're quite easy to discern. So substances on the lens are a huge issue, especially you see them with probes and handhelds. Just someone picks up the probe incorrectly or the handheld incorrectly and ends up rubbing a finger across the lens. They don't think anything of it, but they've just put enough residue there that you're going to lose a lot of your scattering that's coming back into the spectrometer. You can also end up, if you've got a probe system in a reaction chamber, you can also end up getting a deposition on the lens, which again is going to cause the same very similar issue. The microscopes are not immune from this. Again, those of you that work with students might accidentally rub a finger against the optics when they happen to be taking a sample in and out, think nothing of it, and then suddenly they come to you telling you that the equipment's not working properly. First point of call is to probably just give the optics a quick clean with some IPA, and then do another test and see what results you're getting. Again, another issue that you're going to get with with spectrum intensity is due to multi-point scattering. So this is where you end up, the laser travels through several different media. So gases, liquids, so going through bubbles, so foams, emulsions in multi-layer films. This can end up decreasing the potency of your excitation laser, and as such it will reduce the scatter. So we have a little example here, which we have completely solid polystyrene in the green spectrum, and then we have polystyrene packing foam in the red spectrum, which these are normalized spectra, but you can see from the signal to noise ratio, the amount of noise in the red spectrum, how low the signal is in comparison. Some of the peaks are barely distinguishable. And sometimes you will just have lower scattering. So maybe you need to try and reduce the spectrometer temperature if possible. You can see in some instruments do not have temperature controlled spectrometers, but if you are able to reduce the temperature, or at least reduce the temperature in the surrounding area in your lab, having a temperature controlled room is very important. Humidity control is also quite important. But also, if you are using a low number of acquisitions, if you increase the number of acquisitions, you will see an increase in the signal to noise ratio. So here are some rules of thumb which are generally taught, that the limit of detection for a peak, the signal to noise ratio needs to be 3. So, and the limit of quantification, the signal to noise ratio needs to be 10. By using that limit of detection rule, we can only detect 1 peak here, and 2 peaks appear to be completely undetected. Which all of you looking can see that those are 2 peaks. You can definitely see 2 peaks. So really, this limit of detection is a limit of qualification, being able to assess whether, like, using peak fitting to find the Raman shift positions of these will have a very high error due to the noise that is around them, but you can definitely see that there is a peak there. You can also confirm that by repeating the experiment with the same sample and seeing if the peak still remains afterwards, or if it was just either a random noise feature or a background feature. And so, like I say, number of accumulations is a very good way to reduce the amount of noise. In fact, it's my preferred way of reducing the amount of noise. As you can see here, the number of accumulations and the signal to noise ratio go quite hand in hand. I wasn't actually expecting this. I was expecting it. Eventually, you will see diminishing returns. This is actually quite a straight line graph. I commend the student that took this data for me. But eventually, obviously, you will, looking at accumulations beyond 10, I don't normally see an improvement. But if you go too long, then you have other issues with exposing your sample to the laser for too long. Another one that I'm sure a lot of you are aware of is using smoothing techniques, which, as you can see, the smoothing techniques have been able to reduce the amount of noise that we're seeing here and essentially isolate some of the peaks. Now, I know what this substance is, so I know that those 3 peaks that we were talking about are all real. But you will notice that there appears to be almost a broad hump, which could possibly be construed as a peak after smoothing in this red bar region. And also, it appears that the peak positions, at least the peak maxima positions, all slightly shift due to the different smoothings, which again can end up causing an error in your data analysis. So it's something that's worth noting when you're performing your qualification and your peak analysis. Is it worth adding error by smoothing, or just accepting the amount of error that is in your noise currently, which again is dependent on your sample and what you need to be able to do to get a recognizable peak to then perform some analysis on. There are also filtering techniques, which are designed to be less of a smoother. As you can see here, there's from this paper, I've taken a nice example of Savitze-Golay versus finite impulse response. And as you can see, you end up with Savitze-Golay, you can end up with these negative lobes, which obviously do not look real. You also have a massive drop in the intensity of the peaks from both of these, and you end up with some broadening, obviously more severe broadening with Savitze-Golay than with finite impulse response. Again, all of these filterings and smoothing techniques have a lot of different options that you can play around with to direct it around specifically your sample or spectrum. It can become very involved, and like I say, my preferred method of getting rid of these issues is to use a high number of accumulations instead and work from there, because hopefully then I have good enough data that I can just perform peak fitting. So sample phenomena. So we will just do another quick poll just to find out a little bit of information so that I can guide myself into what areas need to be focused here. So if we could have the second poll, please. There we go. So it's all about what Raman wavelength you're using. So what wavelength is your excitation energy? So I've put some examples for each of those. So we have near infrared, so obviously above 700 nanometers, then basically green red visible, which is between 500 and 700, blue visible, which is between 500 and 400, and then ultraviolet, which is everything below 400. And obviously I've left none in there because I know that some of you are not Raman operators and do not have instrumentation, so I thought I would leave that option in there so that you guys can join in. Excellent. So most of you are using green-red visible. It's very expected, to be perfectly honest. It's interesting that we have some UV people, but I'll be gearing most of my talk around the green-red then. So fine. There we go. I have control again. Excellent. So one of the major sample phenomena that you will hear about in Raman is fluorescence. So photoluminescence in the form of fluorescence and phosphorescence are a major issue. You can end up with photoluminescent structures which change based on the wavelength you're using. So here we have a 532 and a 785 system looking at a glass slide, just a simple microscope glass slide. And as you can see, the spectra are quite different. So this can end up being something that you need to take into consideration when using your instrumentation of how is my sample going to behave. Fluorescence, especially in the visible region, so mainly the green, but the blue visible region, you get quite high fluorescence. Red, it diminishes, and then once you go to the near infrared, it diminishes even further, sometimes being non-existent. But it can be a significant contributor in disguising or manipulating your Raman spectrum. But this is still chemical information, so don't give up on it. It may be something that you can use for identification, either in chemometric models or something much simpler. Another route that I personally like to use for ignoring fluorescence, I'll say, is to perform a second order derivative on my data, because then I get the peak information without the fluorescence slope. And I found that to be quite useful in previous research. But another method, which is not going to work on every sample, and very rarely will it work quite as well as demonstrated in this paper. But what you can do is photobleaching, which is essentially where you bombard the sample with your laser irradiation. So you expose your sample to your laser for a prolonged period of time. As you can see here, they tested it for over 3 hours to get their data. But you can end up reducing the fluorescence because you have completely filled the electronic states with energy, which allows the Raman scattering to shine through without being completely dwarfed and hidden by the fluorescence. It's not always this natural log curve either. Sometimes the curve can end up being linear. So the longer that you irradiate for, the much more marked improvement that you see. Whereas obviously with a natural log curve, you start getting diminishing returns quite quickly. I say quite quickly, obviously here it's after about 15 minutes of exposure. And again, this is performed using a green laser. Another sample phenomena is dehydrating your sample. So obviously we're using high-powered lasers, and on very small samples, this is going to excite your water molecules, and they will possibly just evaporate off. And this can sometimes be seen as part of your Raman spectrum, and you can see a shift in peaks, a change in peak shapes, a change in the peak intensities, due to this water leaving. And similarly, if you don't store your samples correctly, if you store them either in a very humid environment, or in fact you put them in a desiccator between analyses, you may also see these differences, which will also create an issue. It's very difficult to really resolve this issue. Again, the way to resolve this is reducing your laser power. Is the real way to try and reduce this. But you can try having humidity stabilized rooms and things like that, but it's a very difficult problem to resolve. Another phenomenon that you will possibly see is essentially your sample heating up. So black body radiation. This is especially seen in your near infrared samples. It will be a sort of rising slope. It's also seen quite similarly in 532, but you can also just see it as a relatively flat increased baseline. It's something to be very aware of. Is how your sample is going to react to high amounts of power, especially high power densities on the surface, because you can of course end up burning and damaging your samples. This is exceedingly common with near infrared lasers, where you have to get a very good signal, you need to put more milliwatts of power onto the sample due to the wavelength to the -4 dependence of the scattering. But on microscope systems using things like 532, if you use high magnification, like times 100, you can end up creating such a small spot with such high power density that you risk causing the exact same damage. It's not always just burning either. You can end up just melting, causing morphological changes, lots of other things. So it's not always where there's smoke, there's fire. Sometimes it's a bit more complex than that. But my recommendation to all of you is start with a low laser power. You'll have a worse signal, but you'll be able to move your power up and you'll be able to see these changes as they progress, and you'll be able to possibly see things that are not visible to you and may not even be visible under your microscope camera. I mean, we have a very nice definition here showing what is and isn't burnt in these, but sometimes it's not quite the same, especially with plastics. So the last section, I believe this is the last section that I'm going to talk about, is instrumental errors. So these are issues that you can have with your instrument itself and things to be aware of. So some lasers you can end up purchasing, especially in modular systems. This can end up being an issue where you've got different parts from different places. You can end up with the alteration of the current to reduce or increase the power actually affecting the wavelength of the laser. And so as you can see here, the different powers seen by the laser due to the different currents put across the laser diode, you end up with not only different peak maxima, but also different shapes. You can see that purple line actually seems to be 2 peaks. There is a solution, in inverted commas, of using optical filters to change the power, so that way you can always be running the same current from your diode. But by placing optical filters in the way, you end up with other issues, and as well as you having less reliable control over the laser power and its replication as time goes on. Another one is your alignment issues. So obviously, if you have one probe and one system, this is unlikely to be an issue. You can optimize that system perfectly. If you have, again, a microscope system, then you possibly have several different optical paths, so several different lenses. Possibly you have different gratings, pinholes, slits that you can change around. And if these aren't all aligned correctly, you can end up with, as I'm showing here, a very different spectral resolution. And that can obviously lead to some confusing remarks about your data, because if you have recorded the resolution of your system using the 100 times, and then you get much broader peaks, and then that could end up, you could end up believing that that broadening is because of some chemical change as opposed to just an instrumental error. Obviously, if you get a intelligent engineer in, they can help you to by aligning your system. So as you can see here with this system, did some realignment of the filter with the pinholes, and we were able to improve the, or in fact make almost the same resolution from each of the optical paths. And the last one that I'm going to talk about, this is less instrumental, but it's a bit similar. Those of you using mapping systems, you will see that you can start mapping, and as you get partway through, you may get to a sensitive part of your sample. This can burn, and then once it moves to the next spot, some of that burnt material may have been thrown up and moved slightly out of the way, or just the area that burnt was larger than the spot analyzed. You will then hit that burnt material, which will then readily burn again, and so you can end up creating this nice snake pattern of burning across your sample. So again, this is monitor your samples. Don't just leave them to work, especially when you're doing preliminary studies. Make sure that you understand how your sample is going to react on the whole before just leaving it to do an overnight experiment. So the main conclusions from all of this are environmental effects. So be aware of them, be aware of the temperature of your room, be aware of the humidity, be aware of the lights. Make sure that you're aware of the environment in which you're taking these spectra and how that can affect your results. Preliminary studies are extremely important, especially to make sure that you're getting the best results for your sample. Don't just assume that because you've done it one way with one sample, that's necessarily going to work with another slightly different sample. You can end up getting very varied responses. I mean, I've done experiments looking at just different glasses or different plastics, and you can end up with very different behaviors from them, even though they are very similar, if not basically identical materials, different pigments and stuff. And you should always view your instrument's behavior as critically as possible. So don't get me wrong, user error does happen, but be aware, maybe something is wrong with your instrument. Make sure that it's well looked after, that you're well calibrating, validating regularly, and regularly talking to your engineers. Having preventative maintenance contracts in place are very useful to ensure that you have the peace of mind to make sure that your research and that your work is going to be repeatable. So I've just thrown in a quick tips for your preliminary studies. So a lot of these I've already said, so this is just to highlight them, but start at a low laser power. I can't stress this enough. Once you've burnt a sample, you can't unburn it. So start at a low laser power. Always perform multiple acquisitions. Preliminary, it's very important to decide on what number of acquisitions you're going to need. Always use more than two. Two is a bare minimum. I prefer to have my minimum at 6 that I personally use. Always use Raman focus over the optical focus. Don't rely on those cameras. it's an easy crutch to rely on, but always make sure that you have good focus on your sample with the laser, not necessarily for the optics. For some samples that are quite sensitive, like especially small powdered samples, it may be worth having your sample out of focus, then turning on the laser and then going into focus. Sometimes the impact of the laser can essentially end up dispersing some of the material and changing what you're actually looking at compared to what you thought was there. And taking images before and after analysis as you're doing this, just quick images. I've done it a few times where I've been analyzing something and then I've looked at it afterwards and I've gone, did it look exactly like that before I put it in? And having those reference images to make sure that you have that clarity, because you've got, I imagine, lots to do and lots on your mind. Take images so that you don't have to try and remember everything you've seen in the past 5 seconds. And so that's the end of my talk. So thank you very much for listening to me. And I will now go have a look in the chat to see if I believe I'll be getting some questions shortly, maybe. I don't know. Oh, the questions pane isn't working. Oh, okay. I've not opened the pane properly. So we do have a question here about fluorescent spectra and what characteristics, what influences the characteristics of the shape and the wave piece. One of the main things that I especially saw on smaller modular systems when I had a lot of problems with fluorescence is essentially what you're seeing is vignetting. So essentially this wavy line is actually induced by the spectrometer, and it's not actually a form of the fluorescence. Fluorescence itself can also have structure, and the structure will change depending on whether or not you have intensity corrected or not your data or your spectrometer. So that's also something that's worth keeping in mind when you're analyzing these. As for the actual structures and behaviors in fluorescence, I'm a Raman spectrometrist. I'm not a fluorescent spectrometrist. So I have limited experience, and most, again, as a Raman spectrometrist, I do spend most of my time trying to avoid fluorescence. I should be embracing looking at it, but we do have problems there. Are there standard operating procedures developed by H2020 projects to define best practices, minimum requirements for QCs, calibrations, validations? As far as I'm aware, they're not available. It is something that we are working on in Charisma. Like I say, Charisma's main purpose and main goal is the harmonization of Raman. So again, defining best practices, that would be a very long book, because there are a lot of different ways to perform Raman. I mean, we've just talked about grouping different laser groups together. You have different setups, so you have probe, handheld, benchtop, so portable system and immovable system, microscopes. Then you have hyphenated systems. There should be, I believe, available online a paper published which has myself as an author, as well as some of my colleagues within Charisma, which is looking at the standardization landscape as it currently exists for Raman. So things from ASTM, the pharmacopoeias, different standards that exist outside of those. So standard reference materials from China and Japan, and where these have shortcomings. Recently seen an update in the European Pharmacopoeia, which has actually started putting a limiter on the resolution that you can have for use in pharmaceuticals, which is fantastic. It's good to know that they are adapting these. So next question is dealing with heating issues. How could we solve this problem to avoid any increase in sample temperature? This is a very complicated issue. Depending on your sample, if it's possible, you could dilute it in potassium bromide, so that you basically have the potassium bromide around your sample to act as a heat sink, to absorb some of the heat energy that your sample is getting. If that's not possible for your sample, then possibly using a cooling plate. So it's either that I believe there are companies out there that do make a little cooling apparatus for samples, but something that's like a large metal heat sink, possibly with some water running through it that's constantly keeping the temperature low in the heat sink, or some fans or something like that, that's extracting the heat then from your heat sink to help reduce the temperature and maintain a stable temperature for your samples. I believe there's more to that question because it's got dots, but I can't make it expand. Is there any way to determine sample temperature? I believe you can determine sample temperature if you can look at the Stokes and the anti-Stokes at the same time. That will depend on your system. We refer to Raman systems having a notch filter, which is to remove the Rayleigh scattering, but quite a lot of them actually just have a band pass because they're designed and set up to only look at the Stokes or the anti-Stokes. They're designed to look at one, and as such they use bandpass filter because that way they can use a cheaper filter to do the same job that a notch filter would do. But if you can look at the Stokes and anti-Stokes, then I believe that should give you information on the temperature of your data. Thank you for the presentation. You're very welcome. Data treatment, work with a portable system. We'd like to ask you about the pre-treatment, like smoothing this kind of data. When is it necessary? Honestly, there are a lot of discussions in this office and within the Charisma Consortium as to when you should be doing different forms of pre-treatment. Things like spike analysis and spike removal obviously is only required when you have a spike, but it's very useful to have to help clear up issues within your spectrometer. As for when to use baseline correction and smoothing and things like this, never. You do need them to, if you need to make your spectra very pretty, then they're very important. If you need to actually be making sure that you're getting accurate chemical information, as soon as you're doing these, you may not be, don't get me wrong, you may be able to reproduce that data over and over again. But if you give me a rolling pin and anything malleable, I can make a sheet out of something. You're not necessarily getting good, accurate data. You're just completely demolishing it and removing all of the actual spectral information. Again, I don't like smoothing. One of the best ways, like I say, a second derivative generally doesn't distort your data that much. You need to know how to read the resulting second derivative spectrum that you create, but that will allow you to have more real chemical information rather than something that is distorted with error. But generally, if you can do as minimal smoothing, minimal baseline correction. So for example, if you just do Y offsetting, so you linearly just shift your baseline down, if that is able to help your data, that is preferred over something more complicated, like asymmetrically squares to then fit a complicated baseline, or even spline or any other technique. So how to check the general status of instrumentation calibration. I mean, there are several different methods. ASTM very usefully has a standard which is E1840 off the top of my head, which has several different materials, 8 in fact. So among those are benzonitrile, sulfur, polystyrene, acetaminophen, which many of you will probably know as paracetamol, and the peak positions for those. Now, again, we have issues with some of those because those were all taken on FT Raman systems, which are fantastic, but do not necessarily behave in the same way that a dispersive system does. The second part of that question is asking is using silicon valid, which is ish. There's no standard for silicon. It does not exist in the standardized landscape. There is a very interesting paper from the National Metrology Institute in Japan, where they've used one of their silicon samples for positron emission, I think. They've used one of those samples to then characterize it using specifically a 633 laser. And they found that they have a very good uncertainty on the silicon peak being at 520.45, because you get a nice sharp peak. That's fantastic, and it's something that we are utilizing as part of Charisma. But if you only check one position on your spectrometer, you only know that that one position is correct, even if it ticks the box. So you need to at least check 3 positions across the spectral range. Another good sample, which I'm sure everyone just has lying around, is diamonds. They have a nice peak at 1332 Raman shift, and again, it's a nice strong peak. And unlike silicon, which ends up heating up with near-infrared lasers, you don't really see the same behavior from diamond, so you end up still having a nice strong peak without this heating black body curve. So no, but again, there is a paper out there if you care to go and find it, and keep posted for updates from Charisma, because we will be planning to create something for these. But also, if you find companies like ELODIZ who can help you with maintenance contracts and calibration of your instrument, then putting a preventative maintenance contract in place is actually very useful. You get a lot of benefit out of that because it's peace of mind. I sound like I'm selling a warranty because that's kind of what I'm doing, but it's true. Dealing with multi-point scattering, could we suspect similar artifacts for micro and nanostructured powders? That is a good question. don't know if you necessarily would be changing several media there. The difference is with micro and nanostructured powders is you are possibly getting a weak scattering because of the volume of analysis, so the actual mass of area that you're looking at. You can end up getting quite weak scatter that because you're only looking at a very small amount. Raman is a very weak technique. It's like, I think it's 1 in a billion photons. So for every billion photons absorbed, you get like 1 photon of Raman scattering. So it's a very weak technique in comparison to the amount of energy that you have to put into it. So that can end up being a limiting factor with looking at certain samples. So sometimes samples do just have weak scatter, but the multi-point scattering, I'm not sure if I would necessarily lump micro and nanoparticles in there. I think they're very difficult to analyze. I mean, I've been trying with some test devices that we've had to analyze some graphene, and that was pretty tricky. But again, you're looking there, you want the high power density, but then obviously once you've got high power density, are you actually then altering your sample? And that's where you do your preliminary study, so you make sure you've got enough sample that you're able to make mistakes, because you will burn samples and change their chemical structure as you do a preliminary study. So you can be as careful as you want, but it is a danger. And the last one is saying thank you. You are very welcome. You're very kind, sir. And yeah, thank you very much for coming, everyone. I'll hang about for a few seconds if there's any more questions that people would like to ask. You're very welcome. Thank you very much. There will be a survey coming out in the coming days, which would be fantastic if I could get feedback from everyone. Feel free to get in contact as well. My contact information is on the screen. If you have some other questions. But yeah, thank you very much for joining me today. I believe, what's the time? Oh, right on time. So I believe that's pretty much going to wrap it up. I don't seem to see any new questions jumping into the chat. So thank you all very much for joining me today. I believe that this will be the end of the webinar. So thank you.